Now let us revise about the coordination compounds. Coordination compounds. Now these coordination compounds are mainly formed by D block elements. And these coordination compounds dissociates in water to give complex ions. It may be complex cation or complex anion. And this complex ion consists of a metal ion or metal atom surrounded by a fixed number of atoms or groups are called ligands. Now ligands are Lewis bases, donates electron pair to the metal atom, and forms a dative bond or coordinate covalent bond with the metal atom. Now ligands can be neutral, means they have a lone pair of electron present but carrying no charge. Examples are like NH3, which is called amine with the double M. We have a aqua, water, and we have a CO called carbonyl. So these are three very important examples of neutral ligands. They can be also called negative or anionic ligands. They have a lone pair as well as a negative charge, and they all ends in O. They have an ending in O. For example, we have a Cl minus called chlorido. We have a OH minus ion called hydroxido, and so on. And we have a Cn minus, one more example, called is cyanido. Now ligands can also be called a monodental ligand having only one donor atom. Monodental example is Cl negative, OH negative, H2O, NH3. All these are examples of monodental ligands. Or a didental ligands having two donor atoms which can donate the lone pair simultaneously. Two donor atoms which donates the lone pair simultaneously to the metal atom. This is very, very important word, simultaneously to the metal atom. Examples are like CH2NH2 and CH2NH2, which is called ethane 1,2 diamine. Ethane 1,2 diamine. Another example is this is called oxalato. They have two donor atoms. Ethane 1,2 diamine has two donor atoms, and this is oxalato, in which we have two donor atoms available and can donate the lone pair simultaneously to the metal atom. This is called oxalato. Then ligands can be called ambident ligands. mean ligands having the same molecular formula, but linked to the metal atom, linked to the metal atom through are different donor atoms. Examples are, we have ONO minus, which is called nitrito O, in which O is the donor atom, and NO2 minus, which is called nitrito N, in which nitrogen is the donor atom. Then in the nomenclature of coordination compounds, how to name the coordination compounds, cation is always named first. Cation is named first, then anion. And if the cation is complex, whichever part is complex, arrange the ligands alphabetically. Arrange the ligands alphabetically. Then name the metal atom, followed by its oxidation state, followed by oxidation state in Roman numerals, and then we name the anion. Now we take some examples now. This is the first example. It's Cr H2O whole 6 and Cl3. Now in this case the cation is complex and this is simple anion. So its name is hexa aqua. There are 6 water molecules, then chromium 3, and then we write the name of the anion chloride. Now next example is this one. It is CO NH3 whole 5, NO2 and SO4. Again the cation is complex but the two different ligands are present. Arrange them alphabetically. So we write pentaamine. So look at the first letter of the ligand, amine A. Then we write nitrito N, because nitrogen is a linking atom. Then we write cobalt, oxidation state is 3, and then we name the anion called sulfate. Now we take one more example. It's a K4 FeCN whole 6. Now in this case your cation is simple but the anion is complex. But it doesn't matter, whichever part is complex you arrange the ligands alphabetically. So its name is potassium, cation is potassium. Then we arrange the ligands alphabetically, hexacyanide, and then we write, if the complex is anion, the metal has to be ending in ATE. So we write ferret in this case, not iron. Ferret followed by its oxidation state 2. So for iron we use ferret, for cobalt we use cobaltate, and so on. But only when the complex is anion. Now one more example. It is Na2 Zn OH whole 4. Now the name is sodium tetrahydroxide, a zincate 2. Now again we are writing zincate, not zinc, because the complex is anion and the zinc ends in zincate. Now one more example is given, and this is copper 2 Fe C2O4 whole thrice. Now in this case the copper shows a variable oxidation state. Now in this case the oxidation state of copper is 2, iron is also 2. So we write the name of the metal first, cation first, so it's a copper. But since the copper shows variable oxidation state, so you have to write the oxidation state of copper also. Then we arrange the ligands, it's a trioxylato. and then we write ferrate, it's a 2. So again, it's a ferrate, it's not iron. Now next is we will discuss about the Werner's theory of coordination compounds. Now according to Werner's theory, the complex or the coordination compound consists of two types of valencies. Two types of valencies, and these valencies are called primary valencies and secondary valencies. So primary valencies are ionizable, means which can be atom or groups which can be removed in the form of ions. Secondary valencies are non-ionizable, means they cannot be removed in the form of ion. Second point, primary valencies are satisfied by anions. And secondary valencies are satisfied by the ligands. And primary valencies are variable, they are not fixed. We can have one anion, we can have two anions, we can have three anions. Secondary valencies are fixed. And primary valencies, they determines the charge on the complex ion. Charge on the complex ion. And secondary valencies, they determines the coordination number and the geometry. Determines the coordination number and the geometry. Now we take some examples. The first example is this: CO, NH3, whole 4, Cl2 and Cl. Now when we dissolve this complex in water, it gives CO, NH3, 4, Cl2 plus and Cl minus. Now this is called a primary valency. There is only one ionizable chlorine. And these are called the ligands. This chlorine inside the square bracket cannot be removed as anion. Now these are called the secondary valencies. And in this case, we have 6 secondary valencies but 1 primary valency. Now we have another example: CO, NH3, NH3 whole 5, Cl and Cl2. Now in this case, we have 2 primary valencies. There are 2 chloride ions. There are 2 chlorine atoms which can be removed in the form of a chloride ion. So 2 primary valencies but 6 secondary valencies. And more the number of primary valencies, more the number of primary valencies, more the number of ions, more the number of unit charges, and more the electrical conduction, higher the boiling point. Higher the boiling point. So second complex given above will have more electrical conduction than the first one. So this more electrical conducting, the second complex is more electrical conducting than the first one, CONH3 whole 4, Cl2 and the Cl. So this Werner's theory helps us to derive the molecular formula. Werner's theory helps us to predict the electrical properties, their colligative properties, but it does not tell anything about the hybridization. So this is about the coordination compounds.